Okay, so now we're about to transition into the next set of material. What we're going to do now is we're going to go into a little bit more detail about the Java thread lifecycle. If you recall our earlier discussions about Android activities, they have lifecycle operations as well. We've got on create, on start, on stop, on pause, on resume, on destroy, all those kinds of good things. And those are basically hook methods that are called back to let your application do something in response to events that the system is aware of. Remember we talked about the template method pattern and how the template method pattern allows an algorithm to be fixed so you can reuse code and then allows certain things to vary without having to change the fixed part. So that's template method and that's used for activities. So we're going to see in the case of threads there's a bunch of lifecycle states as well, but only really one hook method that gets called back, which is the run method. The other things are typically done underneath the hood by the thread scheduler and the thread implementation, as we'll talk about. And so we're going to walk through all of the states that I show up here in the threads. And then we're also going to spend a little time diving deep into how threads are started and stopped on Android. And there's some interesting things that we'll learn about as we do that. When we talk about how threads are started, you'll find out why there's a fair amount of overhead to starting a thread, so you don't want to use them foolishly, use them carefully. And then when we talk about stopping threads, you'll see it's actually a lot more subtle than it appears at first glance to get a thread to stop doing whatever it is it's doing. You don't have to understand all the details in order to how to program Java. So you can program Java threads without knowing all the stuff we're about to talk about. But if you really want to be a full stack programmer, somebody who has a bigger picture view of how things work, this can be helpful. So let's first talk about the state machine for Java threads. So a thread is a fairly complicated piece of software. Back in the old days, in operating systems classes, people would often implement threading libraries. That was the thing you would do back in those days. And it was hard. And we'll talk about why it's hard in a second. One reason why it's hard is there's lots of interaction between hardware stuff and other software, especially layers of software. One of the key parts of understanding how threads work is to understand their state machine behavior. If you take a look at this link, you'll find out the various states that a thread can be in, and that's what is shown on this slide. And if you take a look here, you'll actually see a state machine diagram that gives a different view of this picture here, showing the states that a thread can be in and how they transition between the states. So we're going to walk through each of these states one at a time. The first thing that happens, you start out, in the beginning state with it's the origins of the universe kind of thing in the beginning. And you say new thread. So you new my thread. You make an instance of a thread, which could either be anonymous or not, as we saw in last class. And that transitions the thread into the new state. So the thread has now been allocated. But it's not going to start running. It just has basically some initial memory that's been reserved for it to run. Things don't really get interesting until you call start on your new thread. And when you call the start method, that transitions the thread into the runnable state. And we'll talk later about what happens under the hood to get all the resources allocated. Now, when you're runnable, that doesn't mean you're actually running. It simply means you've been selected as a candidate to run. You actually aren't doing anything yet, you're just ready to run. And there could in fact be lots of things that are runnable, and the operating system scheduler, in conjunction with the virtual machine scheduler, will coordinate to pick a thread to run. And we'll talk about how it picks which threads to run. When a scheduler picks the thread to run, it now transitions into the running state. And once you're in the running state, that's where things get interesting because the run hook method gets called back. And that's where you do your thing. Now, as you can see from this diagram, you can branch off in a lot of different directions once you're in the running state. So let's take a look at some of the things that might happen. One thing that might happen is your run method might call a timed operation like sleep, wait, join, and so on. And sleep, of course, is a method on thread. Wait and join is also a method on a thread with a timeout. And then wait, as we saw, is really sort of more of a method on an object. And when that happens, when you call those things, you go into the timed waiting state. I'm not quite sure what happened with my beautiful picture, but something strange is happening. So we're in the so-called timed wait state. And in the timed wait state, obviously your thread is going to be sort of parked off on some kind of queue until the timer expires. And when the timer expires, whatever you're waiting for, the time expires, it goes back to being runnable again. But it does not transition to go back to running. It just transitions to be runnable. So when a timer goes off, it doesn't mean you're going to start up right away, because there could be lots of other stuff ahead of you on the queue. Okay, so at some point, you're back to running again. And when the run method is called, you might attempt to access a guarded resource. What's an example of a guarded resource? Does anybody know what would be an example of a guarded resource in this context? Lawrence.
Something in a synchronized block?
Exactly. Very good. So you might call somebody's method in a monitor object, and you have to block, you have to wait until you can get into that critical section because somebody else is owning it. So it's like, you got out of your seat to go to the restroom in the airplane, and you get to the restroom and there's a line, right? So you have to wait. So when you're blocked, then again, you're going to be put to sleep on a queue. It's typically, depending on what kind of thing you're waiting on, it might be the entrance queue for a monitor object. It might be a queue that's used for a semaphore, all kinds of different things. And once the resource is actually obtained, in other words, once you become the owner of that lock or whatever you're blocked on, then you go back to being runnable again, and at some point you'll go back to running. And then you might call condition wait without a timeout, in which case you go into the waiting state. Yes, sir?
So whenever you're blocked, is that whenever you get notified that you actually go back to the normal state, or you actually acquire this?
That's actually a different thing. So notify, when you call wait, you are in the waiting state, which is different from the blocking state. Really, they're just different queues. And when somebody else calls notify or notify all, then you transition from the waiting state back to the runnable state again. So whenever you're parked off to the side somewhere, you end up becoming runnable again. Actually, a good metaphor for this is being delayed in an airplane at an airport when you're on the runway, right? So I don't know if anybody here has flown a lot, but if you fly a lot, you inevitably end up in a situation where you get on the plane, you taxi out to the runway, and then they say, air traffic control has put a hold on all flights leaving, so we're going to have to wait here. And usually what happens is and sometimes it's not all flights leaving, sometimes it's flights going to Atlanta or whatever. So then the airplane kind of goes off to the side, sort of parks for a while, and then at some point people say, okay, the air traffic hold has been released, now we get back in line. When the air traffic hold is released, you don't typically start flying. When the air traffic release has been lifted, when the air traffic hold has been lifted, you get back in line, you're now runnable, you're available to take off, but you're actually not taking off. You're not actually using the runway to take off. So that's kind of like being runnable but not running. Finally, if you're in the running state and the run method exits, either because an exception was thrown that propagates out of the run method, or because you ended up with just returning off the end by doing a return or whatnot, the thread then becomes terminated. And at that point, the system will release the resources associated with the thread. Any questions about that? Jake?
Yeah, so could you explain again the difference between getting to the waiting state and getting into the block state?
Yeah, so blocked are typically on things that are like monitor locks or semaphores, things where you're waiting to enter a critical section. So those are resources you have to acquire, like acquiring a lock resource. In that case, the way those things work is the lock mechanism is used to keep others at bay while you do your thing in isolation. So the others that are at bay are people who are trying to wait for that thing, block on that thing, not wait. We'll come back to wait. So when you call a method that's a synchronized method and someone already is inside that method, you have to block on that. And so you're kept at bay. Waiting is the other way around. When you wait on something, you're putting yourself at bay. You're saying, I can't make any progress at this point. I can make no further progress. So I'm going to go ahead and wait, and that will put me to sleep and let other people run so that when they change the world to more like my liking and they notify me, I might have a chance to make forward progress. So blocking and waiting are two different things. Now, they both end up blocking, but the states are different because they're different queues inside the virtual machine and the operating system. Yes?
What is blocking I/O?
So blocking I/O, you would typically, that would be a good example. You would be blocking on like a read or something like that. That would be another example of blocking. In that case, you're blocking on the availability of the data that you're blocking on. I don't want to use the word waiting because that's waiting. So that would be blocking. Yes?
So, why do you have like a waiting and time waiting, not like divided them into the one part?
So why are time things handled differently? Because those are going to be put on yet a different queue that's probably going to use some kind of timer in order to be able to wake things up when it's their turn to go. So that mechanism would be done in a different way than synchronous blocking, which is what we're doing up with the blocking state or the waiting state. So waiting and time waiting are two different states from the point of view of the internal system. Okay, so let's start talking about threads and how you start and stop them. So starting and stopping are sort of the most fundamental things in threading, kind of like being born and dying are two of the most fundamental things in life, right? You know, coming into existence and leaving it, unless you believe in reincarnation, in which case you get to do this over and over again, right? So we're going to start talking about starting a thread. We'll start with starting a thread, and this is going to involve a bunch of interesting things to discuss, and you'll see why you should be thoughtful about using threads. When you call start, it causes a thread to begin to execute its run hook method. And this will end up involving a lot of layers in the Android stack. So it'll involve stuff in the core libraries, the virtual machine, in the libraries, in the operating system kernel, etc. There's maybe probably a dozen different calls at least that get made, and we're going to show you a few of them. So the point of all this to remember is that starting a thread takes time. It consumes a non-trivial amount of resources. So don't do it wantonly. Do it judiciously. Do it when whatever you're going to do is going to take a lot longer to run than the time it takes to spawn a thread. So here are some of the steps. You call start on your thread. That ends up calling the thread start method, which is part of the thread class. By the way, these little path names here are relative to the Android source code, so you can go look at the code if you want to see where it resides. That calls into the virtual machine class, calls another class that's part of the virtual machine class. That calls into a Java native interface method written in C that's part of the Dalvik virtual machine, which is written in C and C++. That calls into yet another method inside of the Dalvik virtual machine. This is a Java native interface method that goes from Java into C. Then that goes inside the actual Java virtual machine interpreter. That ultimately calls pthread create, which comes out of the standard libc library. So if you're a C programmer, that would be where your world would be most obvious. And what happens when you call pthread create is that actually calls down into the operating system. We're not going to look into the kernel level stuff here, but when you call pthread create, the operating system kernel creates a runtime thread stack with those resources we talked about, right? Registers, instruction pointer, various kinds of memory, thread-specific storage, et cetera, et cetera. And it also passes in an object, a function called interp thread start. So when you call pthread create, ignore the handle and the attribute fields. You pass in a pointer to a function, and you pass in a data structure that's typically allocated dynamically. And then that function, interp thread start, is then called in the context of that thread. So in the runtime stack that was allocated when pthread create was called, interp thread start is called, passing in new thread as the argument. And then what happens here is that ends up calling yet another method inside of the Java virtual machine interpreter called dvm call method. And that method finally ends up calling back the run hook method that you define on your thread, which it fishes out from the parameters that are passed in to interp thread start. So we go from the world of Java, the nice, friendly, object-oriented world of Java, into the cold, prickly world of C, long enough to get back in the nice, warm, fuzzy world of Java again. So this is a little side detour that takes place to get into there. Now, this is the way it works with the Java virtual machine implementation. When we all move to the Android runtime, or so-called ART infrastructure, undoubtedly some of these steps will change. Like some of the stuff in the middle here probably will change a little bit. You may not be going through the virtual machine in quite the same way, but I guarantee you that at some point a pthread create call will be invoked, and it'll pass in a pointer to a function, all this kind of good stuff. Okay, so then the point there is there's a lot going on under the hood. That's how you start threads. Let's talk about how you stop threads. So to stop threads, we're going to need to do a couple of different things. So we're first going to talk about stopping threads. Let's see if this thing is mislabeled. This should just be called stopping threads. And it turns out that stopping threads is actually rather hard. Anybody here ever see The Sorcerer's Apprentice, which is a classic movie or it's a scene or a bit from the movie Fantasia, which you can take a look at. And what's the key message of Sorcerer's Apprentice that relates to threads? What does Mickey Mouse have a hard time with in The Sorcerer's Apprentice? Brooms, right? But what's the problem with the brooms? They won't stop, right? The brooms are carrying the water from the well and dousing him, and he's flooding over and stuff like that. So the obvious point there is that starting something is sometimes easier than stopping it. There's no portable way in Java to stop threads involuntarily. You cannot come along and just tell them to stop themselves. There used to be a way to do this, but they deprecated it because it was dangerous. So if you want to stop stuff, then you have to have the thread voluntarily decide to stop, to allow itself to be stopped. And so while you're running, you have to do stuff to make sure that you check to see if you should stop. One way to stop a thread is to use a stop flag. That's why this shouldn't say volatile flag. This should say, oh, I take it back. This is right. Volatile flag is correct. We'll talk about volatile in a minute. So one way to stop a thread is to use a stop flag. So here's a class, myRunnable, that implements Runnable. And it's got some long-running operation in its run method. And to do this, we go ahead and make a Boolean flag called m_is_stopped, which is volatile, and it's set to false initially. And as we'll see later on, volatile is something that's used to make sure that you can do atomic reads and writes without having to worry about race conditions. We'll talk more about that later. So then we define a method here called stopMe, which checks to see if stop, or it sets m_is_stopped to true. And then we simply have to check in our run program whether we've been stopped. And if we have, we go ahead and bail out. Okay, so that's one way to get something to stop itself. Very lightweight, you're just paying the cost of a volatile. There's a downside, though. It's not integrated into the Java virtual machine. And what that means is that any operations that are blocked, Robbie had asked about blocking operations before, like blocking on a read, or blocking on a network read, or blocking on a semaphore or whatnot, those kinds of things will block in perpetuity because they don't know that they need to wake up and check the is_stop flag. So there's no integration with the Java virtual machine. So things that are blocked will be blocked for a very long time. And that can mean it's hard. If the purpose of the is_stop flag is to stop your thread, and your thread is blocked and it won't stop, well, you've defeated the whole purpose of trying to make threads be stoppable. All right, so that was one way to do it. And as you can see, it has a downside. The next way to do it is to use the interrupted method, or the interrupt method. And basically, this is used to have a thread allow itself to be stopped. So when you call interrupt, that posts a request to the thread, and it tells the thread, you've been told to shut yourself down, now you need to shut down. And we'll see in a minute why it's more powerful than using the volatile flag. Here's the documentation on this. So let's assume we have a main program which goes ahead and creates a thread and starts the thread, and then the thread begins to run, and it runs and it calls some operations that block and some operations that don't block, and it does that in a loop. So it's just happily running away, blah, blah, blah. And at some point, the main thread of control decides it wants to interrupt the thread that's running in the background. That's basically the scenario. These methods, process blocking and process non-blocking, need to check periodically to see if they've been told to stop. There's a couple of different ways to do this. Blocking operations, like if you're going to end up calling sleep or wait, operations that are built into the virtual machine that know how to check. They actually know how to check to see whether or not the thread has been interrupted. So if you're calling sleep or you're calling wait or join or other things that are able to be interrupted, those methods will automatically return, and an interrupted exception will be passed in the context where the call was made. So this is a good example of a synchronous exception, right? You're blocked here, and then magically control transfers to an interrupt handler, and you do something or other in response to that. However, not everything you do blocks, right? So some of your code just does some long-running computation where it's never calling read, it's never calling sleep, it's never calling wait. It's just sitting there burning up CPU doing some computation like computing the GCD or whatnot. So if you're doing long-running computations, then you need to periodically check to see if you've been interrupted, and if so, then you go ahead and throw the interrupted exception or otherwise bail out. So the interrupted method returns true if and only if an interrupted request has been received to that thread. So you have to voluntarily check. Any questions about that? Yeah?
Say you're in a synchronized block and you're calling wait and it gets interrupted. When you catch that interrupted exception, are you going to reacquire the lock?
Yes. Okay. Yes. So those, if the lock was not reacquired, bad things would happen. You couldn't write code that was robust.
Okay.
Here's a couple other things to keep in mind. Java thread interrupts don't work the same way that traditional operating system and hardware interrupts work. In particular, traditional interrupts, which are described here, are delivered asynchronously, whereas the ones we just saw are delivered synchronously. Moreover, regular interrupts at the operating system or hardware level preempt the existing thread of control. So the current thread will be running, and then an interrupt will occur, and an interrupt handle will get called typically on the top of the stack that's currently running, and it's handled in a way that you can't ignore. Whereas with Java thread interrupts, you can ignore them, sort of. If you're making blocking calls, there's an interrupt exception that's thrown, but if you're just doing user-defined code, you can not check, and you won't get notified. They have to be tested for explicitly. You have to actually check in your code, was I interrupted or not? So that's different than a regular interrupt. There's a bunch of patterns for dealing with exceptions, the interrupted exceptions. Take a look at this link. You'll learn about these patterns. One thing to do is, if you don't want to handle the exception yourself, simply punt and make the method that you're implementing handle the exception. So in this particular case, or not handle, propagate the exception. So you can propagate the exception by simply not catching it yourself, but making it the caller's problem to figure out what to do. So that's sort of one approach. The great thing about exceptions, by the way, is that they give you an opportunity to punt on handling something without making it completely ignored, in contrast to, say, return values, where unfortunately you can easily ignore them and you don't discover that at all. Another thing you can do is you can perform task-specific cleanup before rethrowing. Here's a little bit of code from the stuff that Mitchell was just talking about a minute ago. So in your program, if you're interrupted in your acquire method, you've got to clean some stuff up and then rethrow the exception. So there's some things you got to do before you throw the exception to clean yourself up. And another thing to keep in mind, there's sometimes when you don't actually have the luxury of throwing the exception. If you're in a run method, for example, that doesn't propagate the interrupted exception, then basically what you need to be able to do is catch the interrupted exception, because it can't leak out of this. And then you don't want to just swallow it. You don't want to ignore it. You go ahead and re-interrupt the thread so that somebody at a higher level can figure out what to do about all this stuff. So those are sort of three different ways. If you go back and read that article, you'll find out more about it. Portable solutions to stopping threads require cooperation between the thread that wants things stopped and the thread that needs to be stopped. Threads have to periodically check to see if they've been instructed to stop. Doesn't handle it in a way that doesn't require some checking, although in some cases, by calling blocking calls, you'll be notified automatically. It's rather tedious to program this, especially if you have to start putting checks into your code to see if you've been interrupted. It takes a long time, but that's the way you're supposed to do it. And if you take a look here, it talks about the ways to stop threads on Android, which are basically the same as they would be on Java. By the way, I was in India one time, not too long ago, and I was walking around a very interesting temple, and I saw a bunch of people sitting out on the grass, cutting the grass with scissors. And I said, wow, wouldn't a lawnmower be a little bit more efficient? And they said, in this particular place, people have to be able to get a job if they want a job. So if they want a job, we're going to have them cut the grass with scissors. That would not be my idea of fun, mind you. But when you have a lot of people that need to be employed, you cut the grass with scissors. Yeah?
There's an old legend about Milton Friedman. Milton Friedman once went to China, and they were having a public works project where instead of using bulldozers, they were using shovels. And Milton Friedman said, to create real public works projects, give people spoons.
So there's an example of how to use thread interrupts. You can take a look at it. You can run it if you want to. And basically what it does is it starts up a background thread that does our little runnable thing like we saw before. And then we go ahead and sleep for a certain amount of time, and we interrupt that thread. And this thread knows to check periodically to see if it's been interrupted, so it'll shut itself down.